We're going to go ahead and investigate a problem that deals with mathematical induction. So with the idea of mathematical induction, you're kind of proving that when we look at a summation of a certain collection of a certain sequence, we want to know if we can actually distill it down into a set formula, or in other words, kind of tie it up into a nice formula so then I can figure out what that sequence would be. So for that summation would be. So for example, if we start off with 1 cubed plus 2 cubed plus 3 cubed all the way to some arbitrary number n cubed. I don't know where I'm going to stop. I'm going to say that the summation is going to be equal to n squared times n plus 1 squared all over 4. The goal of mathematical induction is to actually prove that this is true. So one of the first things that we want to do is we want to verify that this is true in a simple case. If we can't verify the simple case, then there's no point in going on. So we'll say verify with a simple case. And what I mean by simple case is I'm just going to let n be equal to the number 1. So when we verify this case, we'll have the following. We'll say, well, 1 cubed would be equal to, instead of n, I'm going to put 1 in its place. 1 squared times the quantity of 1 plus 1 squared all over 4. This is equal to 1 times 2 squared over 4, which is equal to 1 times 4 over 4, which is equal to 4 over 4, which equals to 1. So that's true. So once you verify the simple case first, then you can move forward. So the next thing that we want to do is we're going to assume the statement is true for the n equaling k case. So what I'm saying here is basically 1 cubed plus 2 cubed plus 3 cubed plus all the way till I reach my number k cubed. That's going to be equal to k squared times k plus 1 squared all over 4. What I want to do now is I want to prove or show that the statement is true for the n equaling k plus 1 case. So in other words, I want to look at the next consecutive case above. So basically the goal here, I want to show, and I'm going to go ahead and try to write this in red on the side, if I have 1 cubed plus 2 cubed plus all the way to k plus 1 cubed, I want that to be equal to k plus 1 squared, because I'm replacing the n with a k plus 1, and I want this to be a k plus 1 squared. So I'm replacing that entire n with a k plus 1, all this divided by 4. This is my goal. So let's go ahead and get to it. So what I'm going to do is I'm going to start off with the above statement, because I know that that is true. That's what I'm assuming is true. And I'm going to add k plus 1 cubed to both sides. I know that this is true because, well, if I add the same value to both sides, then that truth statement is true. You know, for example, if I add 2 to both sides, I'm still maintaining that balance for that equation. So the next thing that we want to know here is, okay, all of the work that I want to show is going to happen on the right-hand side here. So let's kind of keep working there. I'm going to use a little bit of a darker color. So what I can go ahead and do is I'm going to take k squared times k plus 1 squared over 4, and I'm going to make it so that my other term also has a denominator of 4. So I'm going to merge these two. So this is going to be k squared times k plus 1 squared plus 4 times k plus 1 cubed all over 4. And hopefully what you're noting here is that I do have some common terms. I have a k plus 1 squared and a k plus 1 cubed. So this is going to permit me to go ahead and factor that out. So if I do that, that's going to give me k plus 1 squared. And then what I'm left with would be k squared plus 4 times k plus 1 here, because I'm only taking 2 of those k plus 1s out from this term right here. This is all over 4. So I'm going to continue this in red, so because we're almost actually done. So if we were to finish this out, we would have k plus 1 squared. If we clean up what's going on the inside of that quantity here that I'm going to highlight in red, we would have k squared plus 4k plus 4 all over 4. So this in turn, hopefully I can fit it, this is going to be equal to k plus 1 squared times, I can factor that down, that k squared plus 4k plus 4. That actually turns into a k plus 2 times k plus 2, or we can simply say k plus 2 squared all over 4. And right now I'm actually just going to do a quick sleight of hand per se. I have that k plus 1 squared, okay, that I was talking about previously. I'm going to circle it right now. There that is. I still have everything over 4, so there that is. The only thing that looks a little bit different is the fact that I have a k plus 1 squared as opposed to a k plus 2 squared. We'll stare at those two representations really quick. Do you agree that they are the same? Because what I can actually do is I can break that k plus 2 into a k plus 1 squared. And the grouping parentheses that you see there, they're kind of arbitrary, okay? So I don't really need them, but if you want to make it look identical, there you go. You've reached your goal. So we can actually say, we can conclude that, we can say therefore 1 cubed plus 2 cubed plus 3 cubed plus all the way for any case, whether it be the k plus 1 or just n, we can say that this statement is true every time. Okay, and we usually, with a proof, you kind of do a little box and then you shade it, and that kind of represents that you've finished the proof. Okay, so this is a brief crash course into an example of proving something by using mathematical induction. If you have any other questions, please feel free to email me or reach out. All right.